Hey, Math One, Honors Math One, Shasta High School. This is Mr. Roberts right here in room 309. It's the afternoon. What time is it? It's like 4:14. And I want to quickly kind of go through the Chapter 3 study team test. If you were part of a team and everyone was working quickly and you know that you need to kind of review more and you're not quite sure, this is a place where you should be. I encourage you to kind of go through this, pause, um, have a calculator, play with a calculator, think through things, and let's see if we can't get prepared for the test on Friday. So first question, we were given four monomials. You'll notice that there's not any more than one term in each of these, and we're asked to simplify them. Need to get rid of all negative exponents and get rid of things, powers to powers, parentheses, get rid of giant one. So let's take a look at the first one. This first problem says, hey, we have 3, and we're going to raise, we have 3x to the negative second. We're going to raise that to the third power. So what do we have? We have exactly 3 of these things, right? There's 3 of them. How do I know there's 3 of them? Because it's raised to the third. So this is a 3x negative 2 times 3x to the negative second times 3x to the negative second. So I might just write these because there's just 3 of them, right? There's other techniques I can have if there were more, but I could probably even write 5 of those out. Now, when I look at this, what do I have? You can see that there is a 3 times a 3 times a 3. So I'm just going to deal with that part first, right? 3 times 3 is 9 times 3 is 27. So part of my answer is there is the number 27. And I also have x to the negative second times x to the negative second times x to the negative second. That is going to be x to the negative 6th power, right? 27x to the negative 6th power. The problem is there's a negative exponent there. And we've been playing around with this, and I'm just going to start saying this kind of more explicitly now. If I want to get rid of a negative exponent, x to the negative 6th power, I'm just going to multiply that exactly by x to the positive 6th power. Now, I know what you're saying. You can't just arbitrarily multiply something times x to the 6th. It changes it. I know, but I can multiply something by the number 1. So if I have 27 times x to the negative 6th, and I multiply times x to the positive 6 over x to the positive 6, here's the good news. First of all, this thing just equals 1, so I'm not changing the value, right? The new expression I'm going to have is going to have all the same values regardless of the x I give it. I'm just changing its format. And the other thing is that now in this numerator, right, when I multiply x to the negative 6 times x to the positive 6, that equals x to the 0. What is it? It's x to the 0, which equals the number 1. So not only did I multiply by 1, but I turned this negative exponent times a positive same thing into the number 1. What I'm left with is in the numerator, I have the number 27, and in the denominator, I have x to the 6th power. Now, hey, if you're completely done with your test and you're wondering, hey, is there any way I can check if I'm wrong, right? I don't know that you can check if you're right, but if you're wondering, can I check if I'm wrong? Yeah, this is a great strategy. If you're even second guessing yourself, what you might want to do is consider grabbing your calculator and just store what you think a value of x could be. Like I'm going to arbitrarily say 1.25687.4, and I'm just going to store that in x. Boom. So I picked some value of x. What we are saying, right, in our final answer is that this 3x to the negative second times raised to the third power should be exactly the same as this. So I just want to see, are those really producing the exact same outputs for a given x? Here's an arbitrary x, 1.25, etc. Let's look at it. So I'm going to open paren. I'm just going to go 3x raised to the negative second power. I'm going to leave the exponent, close the parentheses, and I'm going to raise that to the third. When I do that, I get exactly this value. Okay, what's your point? Well, now if I look at the fraction that has 27 in the numerator and it has x raised to the negative 6th in the denominator, oh, no, because I'm not thinking it's x to the negative 6. I'm thinking it's x to the positive 6, so that's wrong. Whoops, let me clear that. I'm going to delete u, and I want to delete u because that was a mistype. It's supposed, thank you. That's the number. But yeah, so let me go ahead and do the other one. It's 27 in the numerator and then x to the positive 6. That's what I wrote down. Is that the same? Okay, so look at it. Yeah. What was the other expression? It was, well, you can see it. It's oh, I deleted the other one. It's 27x to the 6. Let me type this other one again. 3 times x raised to the negative second power. Boop, boop. Close that and then raise that to the third. So you can see it produces in both cases this number 8 point blah, 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 blah. If I want to, I can even store a different value of x. I don't encourage this, but like if I was to go 0.5681, store that in x, right? Without typing these, I can go up and I can grab the first expression. Here's what I think the simplified version is. That's what I get, 803. And if I grab this one and do it, I get the same, right? So I know I'm not, I guess what I've done is, if these numbers were different, I know that I would have to be wrong. I would have to be wrong. And I can't say that I'm right, but I can't say that I'm wrong either. So it's pretty good evidence, just as a double check. I don't know that I would do this unless my test was for some reason shorter and I had a lot of extra time. I could think about these things. Let's look at the next problem. The next one, oh, look, we've got this negative exponent, right? This is the tool, right, that we're talking about. I'm going to choose to multiply this by a to the 5th power. Why am I picking that? Because I want this a to the negative 5th to go away. So that's perfectly designed to do that, except I have to put a to the 5th in the numerator. So I am again multiplying by the number 1. In my numerator, I have 5 times a times 5 more factors of a, so that's a to the 6th power. And in my denominator, I have the number 15. And yeah, 5 over 15 is 1/3. You can see it this way, 5a to the 6th over 5 times 3. So I'm clearly left with a 3 in the denominator. So my answer is a to the 6th over 3, a to the 6th power over 3. Let's go to, okay, this one. So again, these are not binomials. It's just a binomial. I've got 4 times 3, which is 12. And then I've got x, 2 factors of x, x squared, times 5 more factors of x. That's exactly 7 factors of x. So I should have 12x to the 7th power. The last one I have here is this. Let's square the denominator first. When I square that, to square something means to multiply it by itself. So I've got 2x to the 4th times another 2x to the 4th. 2 times 2 is 4. X to the 4th times x to the 4th is x to the 8th. So that denominator is 4x to the 8th power, and the numerator is x to the 7th. Can I simplify it? Absolutely, right? Absolutely. I'll rewrite this numerator as just as it was, right? X to the 7th. The denominator, I've got this 4. I'm going to write this as x to the 7th times 1 more x. That is what x to the 8th is, right? It's 7 factors of x times 1 more factor of x. You can see that there is a value of 1 here, right? Now, ooh, I didn't mean to delete that. That was not good. Go back. I didn't mean to delete that. You can see there's a 1 here, right? Now, notice where the 4x is. The 4x is in the denominator. And this giant 1, right, there's a value of 1 in the numerator. So my final answer is 1. It's 1 in the numerator, and in the denominator, I have 4x. All right, question 2. Solve. It says that it's recommended that you verify that your solution is indeed a solution. So I might check that to make sure if it works out well for us. So let's take a look at this. First, I'm going to begin by, let's see, I'm going to use the simplest form of the distributive property twice. So I'm just going to write this as a 3x. There's a plus 5. And then I'm going to write plus 2x minus 12, and that equals 3. And then I'm going to write this as negative 4x, and then a minus 4. All right, so I'm just visually looking at my work. Negative 4x minus 4, 2x, and minus 12. I'm happy with that. Let's collect like terms. 3x and 2x is going to be 5x. And a 5 minus 12 is going to be negative 7. On the other side, I've got a 3 and a negative 4, which is going to make a negative 1 minus 4x. 3 minus 4 is negative 1. Yep. Yeah. And now I'm going to go ahead and add. I'm going to literally add 4x to both sides. So this is going to become 9x minus 7 equals negative 1. Let's add 7 to each side. So on the right-hand side, I've got a negative 1 plus 7 would give me a positive 6. So, and then this side is just 9x. Divide both sides by 9. I get x is 6/9, and 6/9 does reduce. I believe that x is the number 2/3. So if I wanted to check that, I would take 2/3, a fraction 2 over 3, and I would store that into x. There we go. Right? 2/3 is what x is. Now let's look at the left and the right-hand side. So on the left-hand side, it's a 3x plus 5, and then I'm going to add 2 times the quantity of x minus 6. So when I evaluate the left-hand side, it gives me negative 11/3. The left side is negative 11/3. And now let's take a look at the right side. The right side is 3 minus 4 times the quantity of x plus 1. And when I do that, I get exactly negative 11/3. So yes, absolutely, x is positive 2/3 because when I plugged it into the original equation, both sides became negative 11/3. And it is true that negative 11/3 does equal negative 11/3. So it's definitely a solution. Let's look at the next one. It is on the left-hand side rather, I do have a binomial times a binomial. So I'm going to use, I'll use a generic area model here. Why not? We're new to this game. So I need to multiply x plus 3 times 2x minus 1. So when I do this multiplication of x plus 3 times x minus 1, there are 4 distinct regions that pop up. One of them is 2x squared. Then the one next to that is 3 times 2x is going to be 6x. X times negative 1 is negative x. And 3 times negative 1 is negative 3. So the product of x plus 3 times 2x minus 1 is 2x squared plus 5x and then minus 3. Where'd the 5x come from? Right there, right? I'm adding together negative x and positive 6x, which equals 5x. And then on the other side, you can see this was what? This was 2x squared plus 12. The beauty is that both sides have exactly a positive 2x squared, a positive 2x squared. So I'm going to subtract that from both sides. And when I subtract that from both sides, this equation is going to become 5x minus 3 is 12. If I add 3 to both sides, I get 5x is 15. And when I divide by 3, I get x is the number 3. So x should be the number 3. And it said, hey, check it, right? And you can see this is not long. This isn't hard. Timing 3, store that in x, got it. I'm going to go open paren, x plus 3, close parens, open to x minus 1, close it, enter. I got 30. On the other side, I have 2x raised to the second power. And then to that, I'm going to add the number 12. And you can see, look what I get, 30. So when x is 3, both the left-hand side and the right-hand side becomes 3, or 30 rather. 3 is definitely the solution because it makes both the left and right truly equal. They're the same. That's what that's supposed to do. All right, let's go down to question A. And A has some of the strategies that we've talked about in this chapter. One of them is looking inside. And as soon as I see this, I say to myself, huh, that's interesting. This thing inside, I know, has to be the number 64. Why? Well, because if I square 8, I got 64, right? The square root of 64 gives me 8. So this thing inside, right, 12x plus 4 must be the number 64. Because the square root of 64 is 8. So how do I solve that? Well, I'm going to take away 4 from both sides. When I do that, I get that 12x is the number 60. And now when I divide both sides by 60, I get that x is 60 over 12, which turns out to be the number 5. X is the number 5. And you can quickly verify that this is correct. I'm not even going to store x in the variable. I'm just going to say, hey, what is the square root of, so you can see second, and then this x squared gives me the square root template. What is the square root of 12 times 5 plus 4? And you can see it's exactly 8, which is what it should be. So this is a solution. When x is 5, it does produce 8 on both sides. This next one, okay. So our strategy was to rewrite it so that the bases are the same. We're not dealing with logarithms. Rewrite this so that our bases are the same. And then once the bases are the same, it has to be the case that the exponents are equal to each other. So I know, and most of you saw this on Friday, most of you know that that is the same as 7 squared. So I can rewrite this as 7 to the second power. And I'm going to raise that to the 2x minus 1. And then on the right-hand side, I'll just rewrite 7 to the x plus 2 power. So you can see now, this is clearly, right, this is clearly the number 49. So that's why I'm allowed to do this. I replaced or rewrote part of this equation with something that's always equivalent to it. 49 is always the same thing as 7 squared. What I have here now is this pattern where I have a power and I'm raising it to a power. And we have the poster in the room. Like if I have a to the third and I raise that to the fifth, that's a to the 15th power. There are 15 factors of a. 3 times 5. 3 times 5 is 15. Well, I need to do that here. I have to multiply this 2 times this 2x minus 1, right? I need to raise the power to the power. So this is going to become 7 to the 4x minus 2 power. On the other side, it's 7 raised to the x plus 2 power. Okay, so now my bases are the same, right? You can see both of them have a base of 7. This has a 7. If your bases are the same, and these are really equal, right? It has to be that this exponent is the same as this exponent. So what are we going to do? We're going to set those two exponents equal to each other. It has to be the case that 4x minus 2 is the same as x plus 2. Therefore, I'm going to subtract x from both sides. 3x minus 2 is equal to 2. Therefore, 3x has to be exactly the same as 4. Therefore, x is the number 4/3. So I know what x is. It is 4/3, absolutely unquestionable. How can I check that? Easily, I will check that. I'm going to take 4/3 for fraction key 3. I'll just press enter, and now I will store that in x. I find like if I'm doing fractions, it's easier to just press enter. So that's what x is. It's 4/3. Let's check it in the original problem. I'm going to raise 49 to the 2x minus 1 power, and I get this number. And then on the other side, if I take 7 and I raise that to the x plus 2 power, I get this value. So you can clearly see that when x is 4/3, right, both the left and the right-hand side are 656 and some change, right? So that value x is 4/3 is producing equivalent equations. All right, let's move to the part C. On C, we have this situation where we want to bust up a fraction. We want to get so that none of these things have a fraction in them. So I'm going to go ahead and multiply both sides by 2x. And when I multiply both sides by 2x, I'm intentionally placing a factor of 2x in all of these numerators. So each one, so I'm going to write, I have a 3, and I'm going to multiply that by 2x over x, plus 5, I'm going to multiply it by a 2x over 2, equals 7, I'm going to multiply it by a 2x, and then that's all over 2. So look, exactly what we did, right, is I observed that my denominators had an x and a 2. They had factors of x and factors of 2. And I know that if I multiply those fractions, right, by either an x or a 2 or both, it's going to destroy the fractions, right? So by deciding to multiply everything by 2x, this will destroy all the fractions. And just verify, right, this got a 2x, this got a 2x, and although my handwriting doesn't look very good, this also got a 2x. So every single one of these fractions got a new 2x. Now, if I have equal things and I multiply both sides by these equal things, 2x, I get equal things. So this is totally allowed because of my properties of equality. I can push across a factor of 2x to each one of the terms. Well, what do I get out of that? Well, look, this is now right here, this is a giant 1, right? X over x is a giant 1. This is going to become the number 6. What is this? This is the number 1, right? 2 over 2 is a giant 1. So this is going to become plus 5x. And on the other side, oh, you can see it, right? 2 over 2, that's a giant 1. This is going to become, what's the wrong color pen? This is going to become 7x. Okay, so what do we have? Well, if I take away, if I take away 5x from both sides, it's going to become 6 is 7x minus is going to be 2x. And if I divide both sides by 2, right, I get what? I get that x is 3. X is the number 3. Now, it's probably worth checking this, so I'm going to check it, right? I'm going to take 3 and I'm going to store that in x. Got it? Boop. My calculator now thinks x is 3. Let's look at it. On the left-hand side, I have 3, fraction key, x in the denominator, leave that exponent, or leave the denominator, plus 5 halves. And when I take 3 over x and I add 5x, when x is 3, it says 7 halves. Oh yeah, that's what the other side was, 7 halves. So guess what? When x is 3, both sides of that equation become 7 halves. What did we do there? That was fraction busters. We looked at our denominators, decided what to multiply by to get the fractions to go away. What was this? This is rewriting so that I had the same bases. And then once it's rewritten like that, I set the exponents equal, solve them. And this one right here, just looking inside. All right, let's move to the second page. Second page says, oh my goodness, please, first of all, we're going to begin by sketching triangle ABC. Let me do that while it's paused. I believe this is triangle ABC. I plotted those points. I'm at -7, +3, -6, +2, and C is at -4, +4. Next, it says reflect this triangle across the x-axis and label the new triangle with the same thing, but except make the vertices prime. Okay, so here is my x-axis, and I'm going to flip this thing across it. So when I do that, B was going to +2. Now it's going to just go down to -2. So here is my new B prime. A was going to +3. A is now going to go 1, 2 to -3. So here's my new A prime. And C, did I do that right? -7, yeah. And C was at +4. Now it's going to go down to 1, 2, 3. It's going to go down to -4. So here is the C prime. All right, so when this triangle is reflected across the x-axis, this is the triangle I get. And there is a mapping for this, right? There is a mapping rule. And if you want to reflect across x, what is it? It says, hey, the xy's just get mapped to the point where the x values stay the same, but the y's become the opposite of what they are. So that's a mapping rule for that transformation. Next, it says rotate this thing 180 degrees around the origin and label the new triangle. Okay, so when I go 180, when I go 180, that's the same as going 90 and then 90. So one of the things that's useful for the 180, I should grab this ruler. One of the things that's useful for the 180 is if I just look at this B, I can see B was like back 6 and then down 2. But if I go over 6 and then up 2, I'm pretty sure this is where the new, I'm pretty sure this is, come on, draw that. I'm pretty sure this is where the new B goes. So it was on a straight line, and I don't think I can draw that very convincingly with this. I'm not a fan of this ruler now, but it's on that line, and I'm almost positive that this right here is where B double prime would be. And I can do this with all of these, right? For the C, literally if I rotate this thing and I look at it, I know that C is going to be on this line. And I can also do this thing where instead of going down, back 4 and down 4, I'm just going to go forward to 4 and then up to 4. So here's going to be where C is. Oh, actually, this is nice. This is nice. So that's going to be C double prime. And then A is back 7, down 3, but instead I'm going to go I'm going to go forward 7 and then up 1, 2, 3. This is where A double prime is. So actually, I think I've got this rule mapped out in mind. I think if I'm going to rotate 180 degrees either direction, I think the XY is just going to go to whatever X is, it's going to become the opposite of that. And whatever Y is, it's just going to become the opposite of that. So, and then that seems like it's working, because if I look at B, this here is at +6, +2, and before B was at -6, -2. Oh, I like it. Okay, so that's a nice rule to keep in the rule book, right? 180-degree rotation. The X and Y's just get mapped onto the opposite X, opposite Y's. All right, so there's my 180-degree rotation. The last thing I have to do is this translation rule. So I'm going to go, X's are going to be decreased by 5, and Y's are going to be decreased by 2. So I'll use red for this. I'm going to go back 5, 1, 2, 3, 4, 5, and then down 2. So I think this is where C, I guess, triple prime goes. Yeah, and then A is going to go back 5, 1, 2, 3, 4, 5, and then down 1, 2. So this is going to be my A triple prime. Yeah, and then the last one is B, and B is going to go back 1, 2, 3, 4, 5, and then down 2. So then I'm just doing this translation, right? And this is a nice rule here. Where do X, Y's go? X's get decreased by 5, Y's get decreased by 2. So this is going to be B triple prime. The last part of this question is, now that these, let me sketch this. Now that the original triangle was sketched, right, and all the transformations were done, it's just asking us to identify a few points. The first thing, it says, what's the coordinate of C prime? C prime looks like it's at -4, -4. So, right, C prime is at -4, -4. Next point I have is, what are the coordinates of B double prime? Looks like B double prime is sitting right here at 6, 2. And then the last point, what are the coordinates of A triple prime? To me, that looks like A triple prime is where X is 2 and Y is 1. So I'd say 2, 1, 2, 1. All right. On to question 5. Question 5 says, I don't know why the calculator was there the entire time. Question 5 says, hey, evaluate this expression if X is, Y is, and Z is. Okay, so I'm going to go ahead and just right below this try to do in some substitutions. So I'm going to say, look, let's start with, we begin with a 4, but I'm going to subtract what X is, and X is -4. That's all over 9. Plus, we're going to take 3, and we're going to raise that to the -2nd power. And then plus, we've got 12, and I'm going to multiply that times 1/2. So 4 minus -4 is the number 8. So this numerator, if I was going to simplify this, let me turn off this calculator for a minute. If I was going to simplify that, that's going to be 8 over 9. And this 3 to the -2nd honestly caused some issues for some of us. So 3 to the -2nd, we can use the reasoning tools we were just talking about. I can get rid of that as a negative exponent by multiplying it by 3 squared over 3 squared. When I do that, right, in my numerator, 3 to the -2nd times 3 to the +2nd is 3 to the 0. 3 to the 0 is 1. Anything to the 0 power is 1. And down below, I've got 3 squared, or 1/9, right? So this is 8/9 plus 1/9. And then to that, I'm going to add the number 6. Well, 8/9 is 8/9 plus 1/9 it would be 9/9. And 9/9 is 1. 1 plus 6 is the number 7. So I believe this should be the number 7. Yeah, it's the number 7. So the tricky thing I saw was this y to the -3rd. If you're in doubt and it's a number, don't hesitate to just quickly turn on your calculator and say, hey, what is that? What is 3 raised to the -2nd power? It's 1/9. Some of you, we get confused sometimes. We'll look at 3 raised to the, and then we'll do -3 power. Our calculator says, what are you talking about, right? So we can't use this subtraction key when we're trying to make a value a negative number, right? We literally have to do this. Oh, did my calculator make that? What was that? That was interesting. 3 to the minus second power. Syntax error, but when I hit enter, oh, I thought it was making it easy for me to, oh, actually, no, when I hit clear, it put my cursor right where the problem was. Oh, okay. This is worth noting. This is a nice shortcut. So if I make the mistake, if I say 3 to the, and then I do minus second power, enter, syntax error. But if I hit clear, notice it made my cursor flash there at the problem. So instead of being a minus 2, I can do negative, right? So I just hit this button and now it fixed it. I had no idea that it would actually highlight syntax error and then it'll show me where the problem was, so I could just fix that. That's great. All right, let's move on. So next, it says find the slope. Find the slope that goes through. Oh, find the what? Find the slope, just the slope of the line that goes through these 2 points. Okay, this is nice. Find the slope of the line that goes through these 2 points. So slope is my change in y. I'll highlight with this yellow. The change in y values over the change in x values in the corresponding one. It doesn't matter the order, just be consistent, right? So I can take, for example, 154, that's the first point listed, minus 150. And in my denominator, I would do 12, that's the first point listed again, minus a negative 8. I'm not great with this, right? I always am worried, but actually I think I can do this arithmetic. 154 minus 150 is 4. And then 12 minus negative 8 is 20. It looks like I'm getting 1/5. Looks like the slope is 1/5, right? But you know, you've seen me make mistakes with the arithmetic, so let's just run this past our calculator. We'll get clear. I grab the fraction template. In the numerator, I'm going to hit 154 minus the number 150. And then in my denominator, I'm going to take 12, and I'm going to subtract the number negative 8. And interestingly enough, the calculator doesn't require these parentheses, because that's kind of why there's a difference between the subtract and the negative. So this says 12 minus negative 8. And when I press enter, it says, you have 1/5. By the way, fun fact, if I was to go the opposite direction, if I was to take 150 and subtract from that 154, that's the numerator. And then my denominator, I would have a negative 8 minus 12. Notice what I get. Which means what? It doesn't matter which point you start with and which one you end with, right? As long as we are consistent. So I can say, hey, take these and subtract these, or I can say take these and go this way and subtract these. I still get positive. I get positive 1/5. My calculator is hollering positive 1/5, and I'm like, I'm ignoring it because I boxed negative 1/5. Hey, 4 divided by 20 is positive 1/5, right? 4 over 20 is 1/5. My calculator said 1/5 and 1/5. But look at what I've written. Why? Why do I do these things? Why do we do these things? It's wrong, right? It's 1/5. That's what I need to make sure. Okay, good thing I did error checking because I literally made an error. All right, let's move on to the next question. Write these two numbers in scientific notation. Feels like we're understanding this fairly well. So my decimal point was right there at the 3. And because I'm multiplying by 10 4 times, right, I need to move the decimal to the right from right here 4 places. So it's going to be 1, 2, 3, and 4. Beautiful. 32,000. Next one, it says write this one in scientific notation. So you can see I've got 2.7, but in order to make it look like the number above, I have to divide by a bunch of 10s, right? If the decimal is, I placed it there, I need to divide by a bunch of 10s to make this right. How many? By 1, 2, 3, 4, 5. I need to divide by 10 5 times. Except I don't show dividing by 10 5 times. What I do is I show this. But guess what that means, right? That means I'm literally dividing by 10 to the 5th. So that's the number. And I didn't even think about this, but I could go 2.7 divided by 10 raised to the positive 5th power. Yeah, it's the same. Or I could go 2.7 times 10 to the negative fifth power. It's the same, right? So this is kind of cool because we can see, look, if I'm dividing by 10 to the fifth, that means the 10 to the fifth is in the denominator. That would be the same as multiplying by 10 to the positive fifth. It's a good day. Last page. It says, find the equation line that is perpendicular to this line. Oh, and it hits this point. So I've got some point. This point has an x value. This point has a y value. And I want to make a right angle to align with the slope of positive 1/3, right? I need to make a right angle to that one. Well, we know when we go through and we rotate, right, through 90 degrees, I think I'm at 23 and plus 90, I don't know what it is. These things end up becoming opposite in sign and reciprocals. So I know that the slope that I need to use, right, because it's perpendicular to this one, would be negative, and then the reciprocal of 1/3, which would be 3. So this is -3 is my slope. What I don't know is my y-intercept, right? I don't know my y-intercept, but I do know, hey, all lines can be written in the form y equals mx plus b, with the notable exception of vertical lines. I can't do that, right? But as long as it's not a vertical line, you can do it. And this clearly is not going to be a vertical line. So if y equals mx plus b, then it is always the case that y minus the product of m and x will give me my y-intercept b. So that's beautiful, right? It's a great way to figure out what b is. What am I going to do? I'm going to plug the number 9 in for y. Here's 9 minus a -3 was my slope, and my x value is 12. So what do I have here? I've got 9 minus 3, 9 minus -3 times 12, which is what? 9 minus a -36, which is 9 plus 36, which is equal to 45. So I believe my y-intercept is 45. My solution should be y is equal to -3x plus 45. Now, I know, like how do I know? How do I know this is right? Well, one of the things that has to be true is it has to have the correct slope, right? Well, if this has a slope of -3 and this has a slope of positive 1/3, clearly these lines are perpendicular to each other. And the other thing I know is that if I give this line a value of 12, right? If x is 12, it better give me back the number 9, right? Input 12, output should be 9. And yeah, absolutely. -3 times 12 is -36, and -36 plus 45 is 9. So when 12 goes in, 9 comes out. So yeah, it's hitting that correct point. Next question. Okay. It says graph the following equations on one set of axes. Let's see. This first one, I've got a y-intercept at 1, 2, 3, 4, 5, 6, and 7. So I'm gonna just put 1, 2, 3, 4. I'm just gonna put the number 5 here to show that I'm assuming 1, 2, 3, 4, 5. I'm just showing the scale of this, right? Each line is worth 1. So I hit 7, and then it has this slope pattern of down 2 over 1, 2, 3, 4, 5. Down 2 over 1, 2, 3, 4, 5. So that is our first line. And so I can draw that line. And then the other one, I could do this one of two ways, right? One of the things I could do is, I remember reading the math notes section where they talked about x-intercepts and y-intercepts. And I could do that. So like, just a real quick aside, this is just a review. Any point on the y-axis, that's the up and down vertical axis, x would always equal 0. So if I plug in x is 0 into that equation, it'll let me figure out my y-intercept. And the other thing is, any point on the y-axis, right? On the y-axis, no, I'm sorry. Any point on the x-axis, the y would equal 0. So on this line right here, y's are always equal to 0. So if I want to know my x-intercept, I could just throw in y. So what's cool about this is, all of a sudden, if I throw 0 in for x, the equation becomes 4y is 12. Therefore, y is 3. Boop. So I now know my y-intercept happens at 1, 2, 3. And then the other thing I know is that if I throw in that y is 0, if I throw y is 0, this equation becomes 2x is 12, therefore x is 6. So this should be the other point. So I can draw the line through those 2 points. That's a technique, using the intercepts and knowing, my y-intercepts, x is 0, my x-intercepts, y's are 0. Another thing you can do, and I would say like 90% of us did this, was we looked at this equation and we said, hey, I'm going to take away 2x from both sides, so it becomes 4y is negative 2x plus 12. Divide everything by 4, so y equals negative 2 fourths x plus 3, and of course this is negative 1/2. So my y-intercept is 3, and it has this down 1 over 2 pattern. Oh, does it? Down 1 over 2, down 1 over 2, down 1 over 2. I hit it. That's right. Good. So I can see I got the same exact line by following this, finding the slope in the y-intercept, or by using the x-intercepts and the y-intercepts. That's the line right there. And that is the answer for number 9. Almost done? Yeah, we are almost done. We're on question 4. 4 says, express the area of the rectangle below as a product of its dimensions equal the sum of its parts. Well, the sum of the parts for me is always the easiest, so I'm going to say the sum of the parts equals the other way. But the sum of the parts, look, I've got 2x squared, so I'm going to write 2x squared, right? An x squared plus an x squared is 2x squared, plus all the x's. There's 1, 2, 3, 4, 5, 6, 7, plus 7 x's, and then plus the number 6. So there we go. That's the sum of the parts. Those parts add up to 2x squared plus 7x plus 6. Now, product of the dimensions, right? Product of the dimensions. This top dimension, this one along here, this dimension, this is x units long, and this is x units long, and each of these are 1 unit long. So if I look at that dimension I marked with green, that is 2x plus 3. 2 x's, right? It's an x plus 3. And then the other dimension, I'll highlight this in orange. What is this? Well, there's an x here. This is x long, and then plus a 1 and a 1. So this dimension is not a 2x. This dimension is an x. Here's my black. Is an x plus 2. There we go. So 2x plus 3 times x plus 2 equals 2x squared plus 7x plus 6. And if I was to, take this thing, do a generic area model, I would get exactly this product, right? This is legit what I get when I multiply those two binomials. Last question, number 11. It says, use the distributive property to find each product. Use generic area models to organize your work if needed. If needed. I do not think I need this for A at all, right? This is the simplest form of the thing we call the distributive property, x minus 3. When I do it, I'm going to multiply 4x times x, which is 4x squared, and then 4x times negative 3, which is negative 12x. So did not need an area model. 4x squared minus 12x. And then our last problem, oh yeah, I want an area model for this one. So this is a trinomial times a trinomial. So I got 3 things times 3 things. Doop, doop, doop. So divide it into thirds. There we go. Across the top, I'll write an A, a B, and a 2. And down the side, I'm going to write an A negative 2B, and a 1. Okay, so to get the area of each of these pieces, we're going to engage in multiplication. So in this first square, right, to get the area of this thing, I'm going to multiply A times A. And when I do that, this becomes A to the second power, right? And A times another A is A squared. A times B is, I'll just call it AB. And then 2 times A, I just have to put the 2 first, right? It's 2A. Okay, next row down. A times negative 2B. A times negative 2B, I'm just going to say that's negative 2AB. And yeah, I did. I moved around the things that are multiplying. I can because of the commutative property. I like how that looks better. So A times 2B is, or A times negative 2B is negative 2BA, or I wrote down negative 2AB. Same product. The one next to that, negative 2b times b is going to be negative 2, but a b times b is a b squared. Next to that, I've got negative 2b times 2, which is going to be a negative 4b. And then the last row, 1 times a is a, 1 times b is b, and 1 times 2 is 2. Okay, now that we've got the products, right, we need to combine any like terms we have. Well, it turns out that I've got an AB here and a negative 2AB. So those may be combined. They are like terms. Nothing on the next diagonal. But this one, these are like. So I've got a B times a negative 4B. I can combine those two via addition. So for my answer, I'm going to write there's an A squared. And then I'm going to write, let's see, minus, it's a negative AB minus an AB. Where did that come from? It's negative 2AB plus an AB. So that's just going to be a minus AB. And then I'm going to have there's something else I can combine. I can combine the A and the 2A, right? A and 2A is going to be plus 3A. So plus 3A, almost missed those. Those are like terms. Minus 3A. And then I've got a minus 2b squared. I'm running out of room, so I'm going to cheat and grab this thing and just drag it over here. I like the electronic notebooks. That's nice. And then, get out of the way. And then I'm going to go ahead and go, a b and a minus 4b, which would be a minus 3b. Again, I'm adding these now. I multiplied to get the area, but now I'm combining the areas via addition. So a b and a minus 4b is minus 3b, and the last one is plus 2. So, it's very, very useful to combine like terms, right? So if you do have like terms, combine them. The order is not critical here. Like, you could bring a lot of these terms and move them around as long as you bring the signs with them. There has to be a negative AB. It has to be negative 2b squared, and it has to be a negative 3b. But the order can vary, and I can track that well. Well, that's it. How much time is that? I have no idea how much time it is. It's been 47 minutes. That's it for the Chapter 3 study team test. Of course, we are coming up on the Chapter 3 individual test very soon. If you have questions, please stop by room 309 and talk to me. See if I can't help you figure out what's going on. And I look forward to seeing you in class. Goodbye.